Hi, I'm Mrs. Edwards, and today we're going to evaluate limits at infinity. We're going to begin with limits of rational functions. These are rational functions because they're fractions, and in the numerator and denominator, we have a polynomial, like a number x to a power plus a number x to a power, and so forth. Ultimately, our goal is going to be to evaluate limits without looking at their graphs. But first, we're going to begin by looking at the graphs of these functions just to help us understand why the rules work. Then I'm going to summarize the rules, and then we're going to move on to finding limits at infinity for fractions where maybe the numerator and denominator are not polynomials, and then we'll toss in a few more. To sketch the graphs of these three functions, the first thing I would do would be to put in the asymptotes. I put in the vertical asymptotes. All of them have vertical asymptotes at 1 and -1 because of the denominator. And then I also put in the horizontal asymptotes. In this first one, we have a horizontal asymptote that is the x-axis. And then the next one has a horizontal asymptote at y equals 3. And the last one does not have a horizontal asymptote, but it has an oblique, sometimes called a slant asymptote. Finding limits at infinity for rational functions is going to come down to what the horizontal asymptote is. So let's look at why that's true. As you can see, I have sketched in each one of these three functions. But when we find a limit as x approaches infinity, that just means we're substituting in larger and larger numbers and looking for a pattern of their answers. So let's go ahead and create a couple of t-charts where we can see what's happening in that y column as we substitute in numbers that are bigger and bigger. I have substituted 2, 10, and 100 into each one of these rational functions. We're looking for a pattern of what's happening to the answer to that y coordinate column. Let's begin with this first one. As I substituted in larger and larger x's, notice that the answers are getting smaller and smaller. Well, looking at the graph, see how as I substitute in 2, I'm at this height, and I substitute 10, I'll be even lower, and 100, I'll be even lower. But this curve, as we pick x values that are bigger and bigger, it is continuing to decrease, but it's never going to go past this horizontal asymptote. So these answers will never drop below 0. But all of the answers are going to continue getting closer and closer to 0. So the answer to this first limit is 0. Anytime we have a horizontal asymptote that is the x-axis, well, if we substitute in numbers as we go to infinity, the answer is going to be 0. Now let's look at the second example. I substituted in these values and we're keeping an eye on the pattern of what the answers are heading to. If I substitute in 2, I would be at this height, 10 a little lower, 100 even lower, but this curve is getting closer and closer to this horizontal asymptote at 3. So it is never going to drop below 3. But every time I plug in a number that is larger, the height is going to be closer and closer to 3, which is why the limit as x goes to infinity of 3x squared over x squared minus 1 is going to equal 3. The third example, when I substitute values that are larger and larger, 2, 10, and 100, into this function, I get out 8, 30, about 300.03. If I did 1,000, we'd be at just over 3,000. So these y coordinates are getting larger and larger and really large. And that is because as I substitute in 2, and I'm at a height of 8, 10, I'm already to a height of 30. This curve is following this oblique, and so it's skyrocketing. As we substitute x values that are bigger and bigger, our overall answer is just going to keep climbing, and we're not going to head to any specific number, just to a much larger and larger answer. So we're heading to infinity. So the answer to this limit is infinity, but infinity is just a concept, so we often say, instead of infinity, that the limit does not exist. So far, these three examples are illustrating that the answer to the limit as x approaches infinity of a rational function is equivalent to the location of the horizontal asymptote. In the first example, the horizontal asymptote was the x-axis, and that is a height of 0. In the second example, the horizontal asymptote was located at 3, and our answer was 3. And our third example, there was no horizontal asymptote, and the answer was does not exist. So let's quickly review, how do you determine the horizontal asymptote? What's the location? Time for some silliness. I'm just going to give you a visual cue that might help you when you see x approaches infinity. So I have here a pair of infinity glasses, and I am hoping that by putting these on, you will remember this image. Oh my goodness, Mrs. Edwards is so silly. So when I have on my infinity glasses, I want just like a series of connections, again, a little silly. We have glasses on, they are sunglasses. If I have sunglasses on, it's because it's really bright out. If it's really bright out, it's really hot out. And if it's really hot out, I wonder how hot is it? I care about the degree. Infinity, we care about comparing the degree of the numerator to the degree of the denominator. So if we are finding the limit as x approaches infinity or negative infinity of a rational function, and the degree of the numerator is smaller than the degree of the denominator, then our answer is 0. If the degree of the numerator and denominator are the same, well then the answer is a fraction of the leading coefficients, those numbers that are directly in front of the highest degree. And then if the degree of the numerator is larger than the degree of the denominator, well then we don't have a horizontal asymptote, so the limit does not exist. If you want to find the answer to the limit as x approaches infinity or x approaches negative infinity of a rational function, the answer is always going to equal the location of the asymptote. Next up, we're going to need to find limits as x approaches infinity and negative infinity, but rather than having fractions where the numerators and denominators are both polynomials, we might encounter some logarithms or exponential functions, maybe some trig functions sitting in a numerator or denominator. So we're going to still look at these three examples to make some observations so we can then apply that to the more challenging situations. I've made this table where I'm substituting larger and larger x values into a random linear equation, quadratic equation, and cubic equation. We want to look at what's happening to the answers as we substitute larger and larger numbers for x. At first, when we only substitute 1, notice the answer to the linear function 2x plus 4 is the largest value here. And when I substitute a number that's a little bit bigger, our linear one still has the largest answer. But as I start to substitute bigger and bigger numbers, it quickly becomes clear that the cubic answers are going to be substantially larger than the quadratics, and the answers to the quadratics will be substantially larger than the linear functions. So it's a matter of what function is the strongest. In other words, when I substitute in large values of x, what kind of functions will give me the biggest answers? Bigger, faster, stronger. Another way to look at these, instead of just in a small scope looking at asymptotes, we're going to try to look at the bigger picture here. Here the numerator is linear versus the denominator that is quadratic. A quadratic function is stronger. It's going to grow faster. And so it's going to overtake the numerator. Just think of some random numbers that if we make the numerators larger, but they grow slowly, versus the denominator growing, but growing very quickly. Let's divide a few. Let's say 1 over 2. 2 divided by 10. 3 divided by 100. 4 divided by 1,000. 5 divided by 1,000,000. Our overall answer, if the denominator is growing faster than the numerator, the overall answer is going to go to 0. Now, if in this case, the numerator and denominator, they are both quadratic. And that means that their strength is very similar. This extra -1 at the end really isn't that significant if I plug in 1,000,000,000 as x goes to infinity. 1,000,000,000 squared minus 1, the extra -1 isn't going to matter that much. So it comes down to a ratio of their sizes, since the strength of the numerator and denominator are the same. And so we end up with 3 over 1, which is 3. Finally, in this last example, the cubic is stronger than the quadratic. So the numerator is growing much faster than the denominator. Thinking of some numbers where the top numbers are getting larger much faster than the bottom numbers. All right, so let's say 2 over 1, 100 over 2, 1,000 over 3, 1,000,000 over 5. Our answers are going to get bigger and bigger and bigger, and so they're not heading to any specific value, which means the limit would not exist. When we start to encounter other functions sitting in the numerator and the denominator, like logarithms, exponential functions, and so forth, we just really need to know the strength of each one relative to one another. And if the numerator is stronger, well then the limit will not exist. If the numerator and denominator are equal strength, it will come down to a ratio of the coefficients. And if the numerator is weaker than the denominator, then our answer will be 0. Here I have listed a handful of familiar functions: logarithms, square root of x, x squared, and an exponential function. And I have listed them from weakest to strongest. In other words, as I substitute numbers in for x that are bigger and bigger, the logarithm is going to grow the slowest, and the exponential function is going to grow the fastest. I'm going to make a quick sketch of the graphs to illustrate that. Logarithms, whether it's y equals the natural log of x, or which would have a base of about 2.7, if I had log of x, which would have a base of 10, or y equals the log base 15 of x, all logarithms have this basic shape. They get really close to the y-axis in this direction, and then they go through 1. But as they curve over, they grow very, very slowly. I think of logs as the lazy logs. Yes, I'll get there when I get there. Will I ever get to a height of 2? Well, it's going to take me a really long time. Now, square root of x, that function starts here at 0, 0. and it climbs kind of slowly, but not nearly as slowly as the logarithm. Okay, after y equals the square root of x, if I were to graph, let's say, y equals x squared, a parabola, notice at larger and larger x values, our answers are getting bigger even faster. Now notice, square root of x is really the same thing as x to the power of 1/2. This is x to the second. So when x is the base, if the exponent is larger, then the function is going to climb faster. And then the fastest growing function is an exponential function. This is called an exponential function because the variable is in the exponent. E is around 2.71, so this is like 2.7-ish to the x power. And exponential functions, they're actually a reflection of a logarithm across the y equals x line. So their asymptote is the x-axis, goes through 1 here, and then it skyrockets. So exponential functions grow the very fastest. Now, comparatively, if I had an e to the x versus a 10 to the x versus a 20 to the x, of course, the 20 to the x would grow the fastest. Now, let's put some of these functions into some fractions and find the limit as x goes to infinity. On the AP exam, you can expect to find limits as x goes to infinity and negative infinity, particularly on sections that are multiple choice and without calculator. Looking at this first problem, notice the numerator has a logarithm in it. Those are lazy. They grow very slowly. The denominator has a 2 to the x. It also has something linear, like 5x minus 7. But the dominating feature there is the 2 to the x because it's the strongest. The denominator is clearly stronger than the numerator, which means it's going to overtake the numerator, and the answer will be 0. Example number 2, our numerator is a cubic, and our denominator is the square root of x. Cubics are much stronger than the square root functions. So since our numerator is growing faster than our denominator, then our limit is not going to exist. Our third example, these ones can be the trickiest, where the numerator and denominator are growing at the same rate. So sometimes I just mentally substitute in a very large number and compare it. But here, hopefully you can see 2 to the x and 2 to the x, those are the same. So they are increasing at essentially the same rate. The 8x minus 1 and the extra plus 3, those are negligible. They're not going to affect the size nearly as much as the 2 to the x. So we're going to end up using the ratio of that compares the two, and so this is going to end up equaling 5/3. Again, sometimes it is nice to just substitute a few numbers just to make sure you have it. And if I substitute, say 20, 30, 40, you're going to see the decimals coming out in your table to be getting closer to 1.66666, so it's heading to 1 2/3 or 5/3. Here we have two limits that are exactly the same, other than one of them, the x is going to negative infinity, and the other one positive infinity. When an x goes to negative infinity for an exponential function, you need to analyze it a little bit more closely. Let's just put something in the front of your mind. If I had 2 to the power of negative 1, well, that is the same thing as 1/2. If I have 2 to the power of negative 5, Well, that is 1 over 2 to the 5th. Notice as I select numbers that are more and more negative, going to negative infinity, it's actually the denominator that is getting bigger faster, which is why in this case, the answer would be 0. For this particular one, 2 to the x, if I substitute in 1, 2, 3, my overall answer is just getting larger and larger and larger, and we are not getting closer to a single number. So here, our limit does not exist. Here we have an even more challenging limit as x goes to negative infinity. Even though we will likely not have a calculator to evaluate this limit, we can substitute a very negative number and estimate just to kind of get a feel for what's happening. So let's say I substitute in negative 100. That would be 1 over 2 to the negative 100 plus 1 plus 5 to the negative 100 over negative 100 cubed plus 2 times negative 100 minus 9. All right, 2 to the negative 100, that is 1 over 2 to the 100. 1 divided by 2 to the 100 is a very, very tiny number. And a teeny tiny number plus 1 is barely more than 1. So 1 divided by a little bit more than 1 is going to be an answer that is slightly less than 1. So this is just going to slightly less than 1. Now this piece here, 5 to the negative 100, that is 1 over 5 to the 100. 1 divided by an enormous number is a very tiny number. So our overall answer in the numerator is going to be very small as we continue to choose x values that are more and more negative. In the denominator, we have negative 100 cubed, which is going to be a very, very negative number. And then we'll take away another 200 and another 9. So we're going to have the absolute value of the denominator is going to be huge. So we have something small over something that is getting bigger very quickly. So if our denominator is getting larger very, very quickly, then this is going to go to 0. Ultimately, these two examples are going to lead to our last two examples where I hand you the equation of the function. But we just need to first talk about oscillating functions. When you substitute in a number, whether it's going to infinity or negative infinity, but the answers keep changing from positive to negative and positive to negative as we substitute in larger and larger values. Notice in this one here, as I start substituting x going to infinity, I pick 1, 2, 3, 4, 5, 6, 7, and so on. My answers are going from positive answers to negative the further we move to the right. However, our answers are getting closer and closer to the x-axis as time goes on. So as time goes on, this is from both sides getting closer and closer to the x-axis, meaning an answer of 0. So here it's okay to oscillate back and forth across an axis as long as you're oscillating closer and closer as time goes on. Now if I went to negative infinity for this function, well, as I pick values that are more and more negative, we keep getting further and further and further away from the x-axis. So we are never drawing near any specific number. So the answer to this limit would be does not exist. Here I have a function that's oscillating, but it's oscillating the same distance away from the x-axis. Let's say it's going up to 3, down to -3, up to 3, down to -3. Well, as we continue to pick x's that are larger and larger, we're not approaching a single number. We just keep bouncing the same distance across. So since we're not approaching the same value, whether we're going to the right or to the left, the answer as x goes to infinity or to -infinity would be does not exist. So the takeaway is limits can exist at oscillating functions as long as they are oscillating closer and closer to a specific number. Here we have the limit as x goes to infinity of some oscillating functions. As I substitute in numbers that are larger and larger, the sign of 10, 100, 1,000, and so forth, our answers are going between 1 and -1. And when I substitute in numbers into the denominator that are larger and larger, we have a positive answer. So our overall answer is going to be changing from positive to negative and positive to negative. But the overall answer, the absolute value of that answer, the numerator, since no matter how big of number I plug in to sine of x, my answer can't be outside of -1 to 1. So the absolute value of that, my answers are going to be very small. And in the denominator, plugging in numbers going to infinity, the overall answer to the denominator is going to get very, very large. So small numbers divided by a larger and a larger number, they are getting overall smaller and smaller. The denominator is stronger. It doesn't matter that we are oscillating because we are oscillating closer and closer to 0. Now the function sine of x, it just bounces back and forth from 1 to -1. As we go further and further to the right, as x goes to infinity, we never draw near a specific number. We just continue going back and forth between 1 and -1. So since our overall answers are never getting closer and closer to a single value, well then the answer to this limit is does not exist. In summary, when finding the limit as x goes to infinity or -infinity, you want to first consider the strength of the numerator versus the denominator. And often that is enough for you to determine if the answer is 0, does not exist, or a ratio of leading coefficients. Sometimes that's not enough and you have to investigate a little bit. Still, with those big guiding principles, you are going to maybe substitute a very large value for x and estimate the answer so that you get a sense of what the answer is heading to. When you're answering limits as x goes to infinity or -infinity in a multiple choice test, having a sense of what the answer is heading to is usually enough to pick the right answer.